Okay, in this lesson we're going to add to our previous transformations that we did the sine and cosine functions. So we're going to add shifts up and down, left and right. Some more terminology that we're going to review and add to. We've talked about this one before. This is the mean value of the sinusoidal function. That's the average y value of the function. And you can find this by averaging the top and bottom y values. So you're going to average the maximum and minimum y values. Let's see how that works on example 1. So for instance, on example 1, our top y value is 3, and our bottom y value is -1. So that means that the mean value is the average of those two, or adding them together and then dividing by 2, and that's going to give us a mean value of 1. You can also kind of eyeball the mean value because the middle of your sinusoidal function is going to run right through that mean value. Okay? All right, let's get rid of that drawing. And now let's talk about amplitude. Amplitude is the height, the vertical height of the maximum value above the mean value. So remember, just as we were talking about before, our mean value runs right through here at 1. The amplitude is the distance that the sinusoidal function goes above that. So that distance is going to be 2 for this sinusoidal function. The period of the function is the horizontal length of one full cycle or oscillation. So the period of this one can be measured in several different ways. I like to measure period from a maximum to another maximum, or a minimum to another minimum, because that's a really easy point to spot on this function. So it looks like our maximum occurs horizontally at 30 degrees and our minimum at 570 degrees. So that means that that period in between is 570 minus 30, or 540 degrees. The phase shift is the directed distance. Now, directed distance just means negative for a left move and positive for a right move. So it's the directed distance that sine or cosine is translated horizontally. So what we're asked in this question is, what if this is a sine function? This is the only one of these attributes to the graph that it's going to matter whether we look at it as a sine function or a cosine function. What you're going to remember about the shape of the cosine function is that the shape of the cosine function is going from the middle up to a maximum, down to the middle, down to a minimum, and then back up to the middle. That's one cycle of a sinusoidal function, of a sine function. They're both sinusoidal. Now the trick is going to be here finding that place where the cycle starts and ends. So let's actually remeasure the period using this idea right here. It looks like it's hitting the middle right in between -90, and let's zoom in on this just a little bit here. Looks like it's happening directly in between -90 and -120, so that would be -105 degrees. And then it looks like it's hitting that middle again right between 420 and 450, which would be 435 degrees. Let's measure that period again, which would be the length of one cycle, going from middle to middle rather than maximum to maximum. And let's try this again with a subtraction. 435 minus -105 is still going to be 540 degrees. So it doesn't matter how we measure it, we're still going to have the same length. Now, if this is a sine function, the phase shift is where does the sine function actually start? And that would be right here at negative 105 degrees. So our phase shift here is negative 105 degrees. All right, now let's take that same sinusoidal graph, and this time we're going to look at it as a cosine function. Well, if it's a cosine function, the mean value is still going to be the same. It's still going to be 1. That's where the middle of the graph is. The amplitude of this will still be 2. The period, or the length of one cycle, will still be 540. However, where the cycle starts and ends changes what the phase shift is. So if we're looking at this as a cosine graph, cosine cycle starts at a maximum and ends at a maximum. And if we zoom in on this a little bit, it looks like our maximum there is 30 degrees, and then our next maximum is 570 degrees. So for a cosine function, our phase shift is going to be positive 30 degrees. All right, now we're going to use a table of values to actually graph a sinusoidal function. And so we're going to use that same idea that we used in the last section, where we create a table of values based on the order of operations. So for instance, if I am plugging in an x value into this function, the very first thing that I'm going to do with that x value is do the inside of the parentheses, or subtract 60. Then we take the sine of that value, and then we add 2 to that to find our final y value. So that last column is going to represent our y value. So the part of the table that we're really interested in plugging in really easy values for us to work with is going to be that part where we're taking the sine of each value. So if I put 0 degrees, for instance, in the x minus 60 column, then I'm going to take the sine of 0 degrees in the sine of x minus 60 column, and that's going to give us 0. We put our next quadrantal value, 90. Sine of 90 is 1. 180. Sine of 180 is 0. And then 270, sine of 270 is negative 1. And 360, sine of 360 is 0. All right, now we're going to work our way toward the extreme columns. So for instance, if x minus 60 is 0, then x must be 60. Does that make sense? If x is 60, then when we plug it in for x minus 60, we're going to get 0. So we're going to find that leftmost column by adding 60 degrees. That'll give us 150, 240, 330, and 420 degrees. Then the last column, if we have the sine of x minus 60, to find the sine of x minus 60 plus 2, we're just going to add 2 to each of the values in the second column to the right. So adding 2 to each of those, and then we recognize that the first column, that's our set of x values, and the last column is our set of y values. So now let's graph those. And so we have 60, 2. We have 150, 3. 240, 2. 330, 1. And 420, 2. That looks like one cycle of the sine function. So we can connect that with a nice smooth curve, not a sawtooth, right? It's a nice smooth curve, so it doesn't have any sharp turns in it. And then we can also graph the continuation of that cycle. So we can graph a few more cycles. Looks like each time we graph another quadrantal point, we're going over, it looks like 3 of those 3 of those divisions. And so horizontally, that is. And let's continue to do the same thing to the left. And then as we connect that graph, you'll have many cycles of the sine function. Remember though, this is the part that we graphed right here, one complete cycle of the sine function. And that's the only part that we really need the table for. The rest of it you can figure out based on how long it takes one cycle to graph. So now let's get the attributes from this graph. The mean value of this graph is 2. Do you recognize that from the function? That's just the number that we were adding at the end of the sine function. And then the amplitude is 1. And I want to draw your attention to that. 1 is the number that's multiplying the outside of the sine function. It's a hidden coefficient. The period is, let's figure this out. Looks like our cycle ended at where 420 degrees, and our cycle began at 60 degrees. And so the length of that cycle is 420 minus 60, or 360. So our period is 360 degrees, and the phase shift is, where did the cycle start? At 60 degrees. All right, let's try another one with table of values, and then we're going to try to find a way to graph these with a little bit of a shorter method. Okay, this one's a cosine, so let's create a table of values. We've got to plug in our x values, and then order of operations would say, hey, let's add 30 first, because that's the innermost parentheses, and then let's multiply that by 1/2. And finally, let's take the cosine of that. All right, now the values that we normally put in the table, those quadrantal values, are the angles of the cosine. So the step where we're looking at the angles that we're going to take the cosine of is 1/2 times x plus 30. So that's where we're going to put our quadrantal angles. And then for the next column, we just need to take the cosine of those. Cosine of 0 is 1, cosine of 90 is 0, cosine of 180 -1, cosine of 270 is 0, and cosine of 360 is back to 1. Now to work our way leftward, we need to work backwards. If our leftmost column that we have filled in right now is 1/2 times x plus 30. To find x plus 30, we can just multiply that by 2. And finally, to get the last column, subtract 30 off. So that'll give us -30, 150, 330, 510, and 690. All right, let's graph some points. -30, 1, 150, 0. Let's see, where's 150? There we go. 150 is 30 degrees prior to 180. And so 330, -1, and 510, 0, and 690, 1. And we can connect that with a smooth curve. Looks like this one's a little bit more spread out. Let's continue with this same cycle. It looks like we're traveling, 6 divisions on the horizontal axis to get to each quadrantal value. So there's our next one, and there's our next one. So this cycle is a little bit more spread out. Okay, our mean value this time is 0. That's the average y value, the average between the maximum and the minimum. Amplitude still 1. Period this time, if we look at that one cycle was this distance, right? This one cycle right here from max to max for a cosine. So let's take a look at that one cycle, and let's measure the period or the length of that cycle horizontally. And that length is the distance between the 690 at the end of the cycle and the -30 at the beginning of the cycle. So if you subtract those two, you get 720 degrees. Why do you suppose 720 degrees? Because of that little 1/2 that's sitting in front of the angle that we're taking the cosine of. That means that the cosine is going half as fast, so it takes twice as long to graph. Normally it would take 360, now it's taking 720. And our phase shift is, where does the cycle start? That's -30 degrees. Okay, let's generalize some things. Generalizing for a sinusoidal function, if you have y equals a times sine of brackets b times parentheses x minus c plus d, the amplitude of the sinusoidal function is the absolute value of a. Keep in mind that if we're measuring amplitude, it's always a positive number. That's the reason why we're taking the absolute value. If a is negative, that just means that the graph may be flipped vertically. The period is 360 divided by the absolute value of b. Period is one of those things that's also a positive number. Remember the example above where b was a half? 360 divided by a half is 360 times 2, or 720. The mean value is the vertical shift, that's going to be d, and the phase shift is c. A quick note, in order for us to find that phase shift, that input for the sine or the cosine, whatever's on the inside, has to be in that factored form b times parentheses x minus c. All right, so let's do a little practice at finding all of those attributes of a graph. We're finding the mean value, amplitude, period, and phase shift. Let's take a look at A in this example below. Our mean value is that vertical shift, so that's going to be -1. Our amplitude is the absolute value of -2, so that'll be 2. The period is 360 divided by 3, so that's 120 degrees. I think of it this way, that 3 inside of the sine function, the coefficient of the x, that's making it go 3 times as fast, which means that its cycle is reduced by a factor of 3. And then finally, the phase shift is +45. The thing to keep in mind here is the phase shift is the number that is subtracted from x. So if you have x minus 45, the phase shift is 45. If it were x plus 45, the phase shift would be -45. All right, let's take a look at another one. Mean value of this one, we really have a +0 on the end. So the mean value is 0. That's our average y value. And then the amplitude is 5. That's the coefficient or vertical stretch of the cosine. And the period is 360 divided by 4/3, which is the same as 360 times 3/4. 1/4 of 360 is 90, so 3/4 would be 270 degrees. And our phase shift is -60 degrees. That's the number that's subtracted. We have x minus -60. All right, let's take a look at C. Mean value for this one is 3. That's the number that's added to the cosine function. Amplitude is the coefficient of cosine, which is going to be 1. The period is 360 divided by a half, the coefficient of the input. So that's going to be 360 times 2, or 720. And our phase shift is 0, and that's because we have a 1/2 times x minus 0 inside of the cosine function. Last example. Our mean value on this one is actually 4. Now what I'm going to do is I'm going to rewrite this so that it looks a little bit different, so we can see that the 4 is actually being added, right? We have a -7 times the sine of 3x minus 360 plus 4. Same thing, just rearranged, so our mean value is +4. The amplitude is +7, because it's the absolute value of the coefficient of sine. And the period is 360 divided by 3, which is 120. And the phase shift seems like it should be 360, but it's not. The phase shift is what we get when we factor the inside of that sine function. So that's going to be 120 degrees. All right, now let's check out graphing a function in the form a times sine of b times x minus c plus d, or the same thing with cosine. What we're going to do is we're going to do this using a technique that I think you used in Algebra 2, making a new origin using the vertical and horizontal shift. So the very first thing that we're going to do is we're going to make a new origin, and then we're going to create a table of values that just doesn't have the shifts in it. So we're going to take out our x minus c and our plus d. And then we're going to graph the points in the table counting from the new origin. So new origin in example 3a is the phase shift, or the horizontal, comma, the vertical. So our new origin is negative 30, comma, 1. We can mark that one off on the graph. So negative 30, comma, 1 right there. Now let's make a table, and we're just going to pretend like the phase shift and the vertical shift are not there. So we're going to make a table with the x values, and then twice times the x values, just pretend that plus 30 is not there, and then sine of 2x, and then 3 times the sine of 2x. We're just going to take into account those multiplication transformations. All right, in the 2x column, that's where we're going to put our quadrantal values. So 0, 90, 180, 270, 360. And then the sign of those would be 0, 1, 0, negative 1, and 0. And if we keep moving right, 3 times those values would be 0, 3, 0, negative 3, and 0. And now we need to move backwards. So we need to ask ourselves, if 2 times x is equal to 0, then x is 0. If 2x is 90, then x is 45. If 2x is 180, then x is 90. And then you can sort of see that we're going by 45s in the very left column. So that brings us to 180. Now let's just graph our points using that very first and that last column, but we are going to graph those from the new origin. If you remember, 45 degrees is, since our boxes on the horizontal axis or our tick marks are 30 degrees apart, then 45 degrees is 1.5 of those. So we've got 0, 0. That's going to be on top of the new origin. So over 0, up 0 from the new origin. Then over 45 and up 3 from the new origin. So we're at 4 on the y-axis, right, because our new origin was at 1. So we're up 3 from there, and we're right 45 from there. And then over 90 from the new origin, up 0 from the new origin, over 135 from the new origin, and down 3 from the new origin. And then over 180 from the new origin, and up 0 from the new origin. You just have to kind of get ready, get yourself used to graphing from a particular point rather than from 0, 0. All right, let's fill in the rest. And this has a lot of cycles in it, so we're probably going to graph a lot of points here. So be careful. It looks like for each quadrantal value, we're going over 1.5. There's another cycle. And let's continue. There's another cycle. Perhaps on a test, I might not ask you to graph this many cycles. I may give you a window that's a little bit more friendly. Or I may just give you a graph that just doesn't have as many cycles to graph. That may be a better way to do this, because I don't really want you spending a lot of time on a test worrying about graphing additional cycles. But I do like this for homework because it does kind of give you that idea about, since we're graphing all of these in the same window, that there really are more cycles of this graph, or it goes like twice as fast as a normal graph. And by normal graph, I mean the parent function. And let's see if I can do a good job with this one, hopefully. And you'll kind of notice, actually, if it doesn't look right. There we go. All right, let's check out the next one. Y equals 2 minus 3 times the cosine of 1/4 x. So you may want to even rewrite the function -3 times the cosine of 1/4 x plus 2. So our new origin is going to be the point 0, 2. And so we can mark that one off right here. And that's because we don't have anything subtracted from on the inside of the cosine, subtracted or added. So now when we're making our table, we're just going to pretend that that vertical shift of 2 is not there. So x, 1/4 x, the cosine of that 1/4 x, and finally -3 times the cosine of that 1/4 x. The quadrantal values are the values that we're going to take the cosine of, so 0, 90, 180, 270, 360, and then we're taking the cosine of those, 1, 0, -1, 0, +1, final column times -3. So that's going to flip our signs. And then working backwards from the leftmost column, to the leftmost column, we have to divide by a quarter, which means we're multiplying by 4. So 0, 360, 4 times 180 is 720. Looks like we're going by 360s, right? So the next one's going to be 1080, and the next one's going to be 1440. And so let's graph those. 0, -3. So that's 0 over 3 down from the new origin. 360 over 0 down from the new origin. 720, 3 up from the new origin. And it doesn't look like we're going to graph a whole cycle here. It looks like we only got a half a cycle in there. Let's go backwards and see if we can get some more in. So it looks like we're going by 360s here, right? So then the next point would be backwards that direction for a cosine graph. Okay, so this one was very spread out. All right, let's try one more. Before we try to determine what the new origin is, we're going to want to rewrite this function. So we may want to rewrite it this way: y equals 2 times the sine of 3 times x minus 60. And then we have a -3 afterward. So it looks like our new origin is the point 60 degrees, -3. So let's mark that one in. There's our new origin. Then we're going to make a table of values, and we're going to pretend that those shifts are not in the equation. So we've got x, we've got 3x, we've got sine of 3x, and finally 2 times the sine of 3x. Quadrantal values are the values that we're going to take the sine of, so that would be 0, 90, 180, 270, 360. And then we take the sine of those, 0, 1, 0, negative 1, 0. 2 times those for the final column. And then in order to move leftward, we have to divide by 3. So 0 divided by 3 is 0, 90 divided by 3 is 30, 180 divided by 3 is 60, and you can see that left column is just going by 30s, right? So 90, 120. All right, let's graph some points. So we're going to use our first and last columns. So 0, 0 from the new origin, over 30 up 2 from the new origin, over 60 up 0 from the new origin, over 90 down 2 from the new origin, and over 120 down 0 from the new origin. So it looks like there is one cycle of this graph, and then we can just fill in the rest here. Just going to keep going up and down. Until we get to the end of the graph. So let's fill in a little bit more. This one is a really short cycle, so there are a lot of cycles to graph. There we go. And let's move to the left as well. And then we're going to connect with a nice smooth curve. And I'm doing a lousy job with this. You're going to do a better job with your pencil. All right, the last thing that we're going to do is we're going to write an equation for each sinusoidal function. So we're going to base it on some of these attributes that we've seen before. So I have some tips on this. I think it's probably easiest to write an equation for a cosine function than it is for a sine function. And the only difference between the cosine function and the sine function is going to be a phase shift. All of the other attributes are going to be the same. It's just that it's easier to identify a maximum, and that's where the cosine function starts at a maximum. So let's take and let's just go maximum to maximum, for instance. And that would be one cycle of a cosine function. So it looks like our cosine function starts here at negative 60 and ends here at 120. So it looks like we've identified our phase shift, right? That's our C value. And then the period, if I can spell that right, period is equal to 120 minus negative 60, or 180. That means that our B value is going to be 360 divided by 180, or 2. So our B value is 2. Now let's find the output values, the things that are happening outside of the cosine function. Looks like that midline is right there at 1, and that our amplitude, the distance above that midline, is 3. So if we write the cosine function based on that, we'll have y is equal to 3 times the cosine of 2 times x plus 60. If our phase shift is negative, we're going to have a plus 60 inside the parentheses, plus 1. So there's an answer for this particular graph. Now I do want to point out that it's not the only answer. Suppose your classmate did the same thing, but let me get rid of all this other junk here on the graph. Instead of doing what you did, or what we just did together, they said, you know what? I'm going to go from here to here, from a minimum to a minimum. Two things are going to change. Since we're going from a minimum to a minimum, the cosine function is inverted, so we'll have a negative 3 times the cosine of 2 times, and the second thing that'll change is our phase shift. Now our graph is starting its cycle at 30, so we'll have x minus 30 degrees plus 1. Suppose another classmate said, hey, I want to do this just a little differently because I want to express my individuality, and I want to do this as a sine function. So they start here and end here, and we have a sine function. Now that's a right side up sine function, so that means our 3 is going to be positive. But this time, our phase shift is also going to change. Our phase shift is somewhere between 60 and 90, right? Halfway in between that would be 75. So there's another possibility here, y equals 3 times the sine of 2 times x minus 75 degrees plus 1. The possibilities are actually endless depending upon where you start and end your cycle. So just something to be aware of. There's multiple answers. All right, let's check out the last one here. Let's do the easy thing, I think, and let's use a cosine function. So a cosine function is going to go max to max. And this appears to start at 30, so there's our phase shift, and ends at 270. And that gives us a period of 270 minus 30, or 240. That means our b value is 360 over 240, which reduces to 3/2. So we have y equals, and now we need to find our amplitude and vertical shift, right? So it looks like our vertical shift here, where's the average y value, is at 2. And our amplitude is also 2. So y equals 2 times the cosine of 3/2 times x minus the phase shift of 30 plus 2. And recognize there are multiple answers, but that one's a perfectly good answer. All right, that's it for the lesson.